In this segment, we'll talk about three parameters: volume fractions, that of the fiber in the matrix, weight fractions, that of the fiber in the matrix, and the density of the composite. These are going to form a critical part of being able to do the micromechanical analysis of a lamina so that we can find our 13 parameters. The 13 parameters being the 4 elastic moduli of a lamina, 5 strength parameters of the lamina, and 2 coefficients of thermal expansion and 2 coefficients of moisture expansion. So let's look at the definition of volume fractions. So this is fiber volume fraction. It is defined as the volume of the fiber divided by the volume of the composite. This is the matrix volume fraction, which is defined as the volume of the matrix divided by the volume of the composite. Now, of course, the addition of the two volume fractions of the fiber and the matrix will be equal to 1. And then, of course, the volume of the fiber plus the volume of the matrix will be the volume of the composite. Now, here we are defining weight fractions. So this is the fiber weight fraction. It is defined as the weight of the fiber divided by the weight of the composite, which will be same as the mass of the fiber divided by the mass of the composite. So, of course, when we're talking about ratios, it does not really matter whether we call them mass fractions or weight fractions. But if we are calculating the weight, then of course it have to multiply by the acceleration due to gravity, the mass. So we need to be careful about our definitions and also how what we call as weight and what we call as mass, we cannot interchange it. But so far as fractions are concerned, yes, they will be exactly the same. So this is the definition of the matrix weight fraction, which is the weight of the matrix divided by the weight of the composite, or we can call it the mass of the matrix divided by the mass of the composite. And of course, the two weight fractions of fiber and matrix, or if you want to call them mass fractions, it'll be equal to 1. And then the weight of the fiber plus the weight of the matrix will be equal to the weight of the composite. Or you can say that the mass of the fiber plus the mass of the matrix is equal to the mass of the composite. It depends on what you want to use. But again, keep in mind that the weight fractions are same as the mass fractions. Let's go and find out the derivation for density using fiber volume fractions and mass and matrix volume fractions. So we know that the mass of the composite is same as the mass of the fiber plus mass of the matrix. So we also know that density is mass over volume, right? So we can say that, hey, density times volume is the mass itself. So if we use this here, we're going to get that the density of the composite times the volume of the composite is equal to the density of the fiber times the volume of the fiber plus the density of the matrix times the volume of the matrix. Now what we're going to do is we're going to divide by the volume of the composite on both sides, and we're going to get something like this. But we recognize that this is the definition of the fiber volume fraction, and this is the definition of the matrix volume fraction. So we get rho f times Vf plus rho m times Vm is the density of the composite. Now, of course, keep in mind that Vm is nothing but 1 minus Vf, because the total volume fraction of the fiber plus the volume fraction of the matrix should be equal to 1. So we can rewrite this in terms of the fiber volume fraction, but this is okay that this is the formula for calculating the density of the composite. Let's go and see how we can calculate the density by using weight fractions. So rather than starting from that the mass of the composite is equal to the mass of the fiber plus mass of the matrix, we're going to start with that the volume of the composite is equal to the volume of the fiber plus the volume of the matrix. Now again, we go back to our definition of density, which is mass over volume. So in this case, we'll get volume is mass over density. So that's what we're going to use here, that the mass of the composite divided by the density of the composite is equal to the mass of the fiber divided by the density of the fiber, mass of the matrix divided by the density of the matrix. That's all coming from here. So once we have that, what we're going to do is we're going to divide by MC, which is the mass of the composite on both sides. That's what we're going to do. And the reason why we write it in this particular form right here in the numerator is because you can recognize that this is the definition of the weight fraction or the mass fraction of the fiber. And this is the definition of the weight fraction of the matrix or the mass fraction of the matrix. So that's what we're going to get. So we have a reciprocal relationship here for the density of the composite in terms of the weight fractions. Let's go and see how volume and weight fractions are related to each other. So we want to see, hey, what is the relationship between these four quantities? So we know that the volume fraction, the weight fraction of the fiber is the mass of the fiber divided by the mass of the composite. That will be equal to the density of the fiber times the volume of the fiber, density of the composite, volume of the composite. And what is this the definition of? Fiber volume fraction. So it will be rho F by rho C times V uppercase VF. So same thing we can do for the weight fraction of the matrix. It will be mass of the matrix divided by the mass of the composite, which will be rho M multiplied by Vm, rho C multiplied by Vc. Again, this is the definition of the volume fraction of the matrix. So we get rho M divided by rho C times Vm. So that's how the volume fraction, you can go back and forth between the volume and weight fractions for fiber and matrix. And of course, we know that the density of the composite is nothing but this formula here, or in terms of the weight or mass fractions, it is just this one. So we can either use this one or this one to calculate the density of the composite for going back and forth between the weight fractions and the volume fractions. And that's the end of this segment.